Hello all, welcome to Kalike, and in this session today we are going to explore about electrostatics. Now, I have some question to you before we learn more about electrostatics. Have you ever wondered or have you ever noticed a tiny shock or experienced a tiny shock or a small shock or even heard a crackling sound when you're wearing a sweater in a dry weather or especially winters, and when you're trying to take your sweater off, you might have felt a tiny shock, or you might even have felt some crackling sound that appears. Have you ever experienced this? If so, then these are very simple examples or illustrations of what is known as static electricity or electrostatics. Now, how do we understand this, or why does that really happen? Okay, now to understand this, you need to basically understand the fact. For example, when you're wearing a nylon cloth or a synthetic cloth for that matter, or even when you're wearing a woolen cloth like a sweater or a sweatshirt, then when you're trying to pull it off, you see that cloth is in contact with your body, so it is obviously when you move, the fabric rubs against your body parts, transferring something called charges. So the body, every body is made up of atoms, and as you know, atoms are made up of electrons and protons, which are also referred to as charges. So when one body rubs against the other, or one fabric or one material rubs against another material or a body, there will be a transfer of charges. So when the sweater or when a synthetic cloth that you're wearing rubs against your body, then you see that there is a transfer of charge, or there is some charge that is being collected, there is some charge that is being formed on a particular substance. Now, when you see, why do you experience that clarking sound or a tiny or a small shock? Why does that happen? That generally happens when you're wearing such a cloth on a dry day or a winter day, and you're trying to open the door holding the metal knob of the door. Or let's say when you're sitting on a car seat for a long time, you're traveling, and then you come out of the car, you met the metal body of the car or the metal handle door of the car, then also you see a spark jumps, or you feel a tiny shock, and you pull your hands away very immediately. Now this happens because, as I said, now in the car, for example, you've been sitting for a long time and your hands are rubbing against the seat of the car, or they're in contact with the seat of the car for a long time. Now when two objects are in contact for a long time, there will be exchange of charges. The charges from that fabric of the seat get transferred to your hands. Now these charges need to be released out into the atmosphere, or they need to go out into the atmosphere. But on a dry day or during winter, you see air molecules act as insulators, because the humidity in air is comparatively less as compared to as any other day. Since water molecules are less surrounding in the surrounding air, there is no way for these charges to escape out from your system, from your body. So since your body is a conductor, now when these charges get collected on your body and you touch a metal knob, or when you touch a doorknob, or when you touch the metal part of the car, the metal handle of the car, what happens is your body, through your body, they jump into the air, they escape into the air. While doing so, you feel that sense of tiny clarking sound, or you can see the charges jumping on. That is why you feel a tiny shock or a small shock that we experience during winters or dry weathers. Okay, so this phenomena happens in a big form in nature, which we call lightning. So what happens during lightning? During lightning, they also definitely happen when the clouds are heavy with static charges. These charges, which cannot move or which cannot be passed on into the atmosphere surrounding them, they are static at a particular place, they are stuck or they're collected on a particular place, because there is no conductor for them to release those charges into the atmosphere. So when such a thing happens, when the cloud really becomes heavy with such static charges, and when it is raining, and when it starts raining and the ground, the earth acts as a very good conductor. So through the water molecules, these the water molecules which are falling from the sky, they act as a conductor, and then these charges easily jump on to the surface of the earth. So these charges are what are referred to as static charges. So electrostatics is basically the study of charges, electric fields, electric potentials with charges being at rest. So here we assume the charges are at rest or they are static at a particular place, and the whole study of this branch of physics is what is referred to as electrostatics. Now, how were these charges discovered? Who was the one who first came noticed it? So did it happen some 100 years ago, or 300 years ago, 1000 years ago? No, it actually dates back to somewhere around 2500 years ago, around 600 BC, when the Thales of Miletus observed that a material called amber. So what is amber? Amber is a fluid kind of structure, or rather it's like a resin or like a glue kind of structure that usually comes out of the tree. Okay, so this amber, when it was when it was rubbed against silk or fur or wool, and then you saw that when it was brought closer to feathers, it attracted pieces of the feathers of the birds. So I repeat, when amber, a material usually found in trees, which is just like the glue or the rubber that we get from the trees, it was rubbed against a material called silk or wool. It was found that amber could attract pieces of feather. Now this was something really strange. How does this have that magnetic property? Like just like you take a comb, you comb your hairs, and then you comb it for a long time, and you take the comb near pieces of paper, tiny pieces of paper. You see that the comb attracts pieces of paper. How can that magnetic property or this attractive property come into place? How does that happen? So similar thought came to his mind, and how can this happen? How can this material suddenly attract pieces of feather? Is there some magic around here? Does it turn really magical? So that is where the first discovery of these electrostatics happened, or electrons happened. So amber was the material which was found in the trees, trunk of the trees, and then this amber is in Greek was what was referred to as electron, which we now to refer to as electron in chemistry and in physics, in science basically. Okay, so amber was the first point where people observed that yes, one thing can attract the other thing. Now eventually what happened was people started experimenting, scientists started experimenting a lot of things. So what they did was they took a piece of glass rod. Okay, imagine this is a piece of glass rod. They took a piece of fabric of silk. So this is silk and this is glass. Now they took this piece of silk and rubbed it against the glass rod, rubbed it thoroughly for some few minutes, and then they saw that after some time this glass rod could attract some pieces of paper or some other thing. It could attract some pieces of paper or some other thing. So that was again strange. Now what they did was they took another glass rod, they rubbed it with silk, they rubbed it with the same silk cloth. Okay, now they try to bring these two glass rods together. So this is one glass rod, this is the glass rod 1, this is the glass rod 2. So glass rod 1, okay, was brought near the glass rod 2. Okay, strangely, instead of both getting attracted to each other, a surprising fact was observed that both started repelling each other. They didn't want to be close to each other. They started repelling away, going away from each other, and that is when people were surprised. Instead of getting attracted, why are the glass rods getting separated or moving away from each other? This was a phenomena that was not observed. That is when the scientists came with an analogy that when a piece of silk cloth is rubbed against a piece of glass, a certain type of charge is transferred to this. Similarly, when glass rod is rubbed against silk, a certain type of charges are transferred to silk. So when the same, so probably the certain type of charge or certain type of charge was transferred to glass one, same type of charges were transferred to glass 2. Since both had similar kind of charges, when you brought them together, instead of they getting attracted, they wanted to move away from each other. They were making faces against each other. They were not attracting, they were repelling from each other. So that is when they came to know probably there is not only one kind of charge, there must be different kinds of charge. So things with different kind of charges probably attract each other, and things or materials with different kinds of charge probably attract each other. Okay, so it was Benjamin Franklin who came up with the idea that there are only two kinds of charges. The first charge is what is referred to as positive charge, and the second charge is what is referred to as the negative charge, which we refer to as the electron now. So the negative charges and positive charges are the two charges that exist in nature. So when objects have opposite kind of charges, they kind of attract each other, and when they have similar kind of charges, they tend to move away or repel from each other. So now this brings us to a very simple rule in electrostatics with regards to charges, that like charges repel, like charges repel, and unlike charges attract. So similar kind of charges. So if you have positive and positive charges, if there are excess of positive and positive charges on a body, those materials do tend to repel from each other or go away from each other. Whereas metals or whereas materials with unlike charges, if they have a different kind of charge like positive charges and negative charges accumulated on them, so they tend to kind of attract each other. Okay, now this leads us to something called an experiment which was done called the Gold Leaf experiment. The Gold Leaf Electroscope. So this is a device which is used to measure the amount of charge contained on a body. So that generally houses, or this has has a metal box, something like this. So this has a metal box, right? So where you have a metal rod, okay, there will be a metal rod with gold leaves inside. So there are gold leaves here and here. Now when you bring, there will be a metal here, a particular kind of metal. Now you bring silk, a piece of silk cloth, and come and rub it against the metal knob. You see that the charges do get transferred. You are transferring some charges from the piece of silk cloth. Suppose it has positive charges. Now what do you do when you rub it? There could be some charges, or let's say there are positive and equal number of positive and negative charges, but what happens, there could be some electrons that are revolving freely in this particular atom. So when you bring this piece of cloth and rub it against each other, if there are two extra electrons, or if there are two electrons that are moving freely in this particular cloth, you are basically transferring those two free electrons to this. So this loses two electrons, whereas this metal rod gains two electrons, right? So it is losing two electrons, and these two electrons are being transferred to the metal rod. They flow down the metal rod, and these two get charged. So since they both have similar kind of charges, they repel each other. So the degree to which they diverge gives you the measure of the amount of charge on the metal rod. It will tell you how many electrons were transferred. So this is one kind of experiment that was conducted, or an instrument that is in place, that was in place long time ago, which was used to measure the degree, the amount of charges that were transferred. So now, what are conductors and insulators? So, well, conductors are materials where there are free electrons available. Electrons are freely moving in the material. Okay, so conductors are basically which allow easy passage of electricity. So the electrons, there will be freely available electrons. One or two electrons are not tied to the nucleus. They are freely available, revolving around the atom. Such materials are what are known as conductors. Human body is a conductor, and then water is a good conductor, ground is a good conductor, whereas all metals, most of the metals are very good conductors of electricity. What are insulators? Insulators are the materials which do not allow free passage of electricity. They do not have free electrons available or revolving around the nucleus of an atom so freely available. We will learn more about it when we study a chapter called semiconductors, and hence I'm not explaining or going into the details of how the free electrons are available. You'll also learn more about it in chemistry. We will explore the same more in a chapter called semiconductors. Okay, so now that we know, conductors are materials which allow free passage of electricity, easy passage of electricity. Insulators are materials which restrict or which resist the flow of electricity through them, because there are no free electrons available revolving around the nucleus of an atom, right? So what are the examples of insulators? Examples for insulators are like plastic comb that you have, generally plastic and other some of the non-metals. Some these kind of materials, wood, plastic or rubber, these kind of materials are generally they do generally come into the category of insulators. Now let's take the example. If you have a comb, let's say you have a comb, you rub it against your hair. So this is piece of hair, somebody's hair, imagine. Okay, so you rub it against the comb for a long time. You take a brush, you rub it, you rub your the comb against your hairs, and then you bring the same comb to pieces, near the pieces, tiny pieces of paper. You see that this comb attracts tiny, they literally jump and fly, and they go and burn a few pieces of paper, go and get attached to the comb. Why does it happen? Although this is an insulator, but this is a comb which is an insulator. This happens because in an insulator, since there are no free charges available or no free electrons moving around the nucleus, these electrons are tied. Whatever, when you rub the brush against your comb, there is a transfer of charge from your hairs to the comb, or from the comb to the hair, and all these charges go accumulated and sit on the comb. There are excess charges, but these excess charges cannot go into the atmosphere directly. So what happens when you bring some other material which might have some other charge, this gets a medium, so you are allowing a free passage. So there will be, you see, these get attracted, So that allows a free passage of movement of electrons, right? Now, what if I have a metal comb? Let's say this is a plastic comb. Suppose if you have a metal comb, let's say, what will happen if I rub it against the head and bring it again the pieces of paper? You surprisingly see that the metal comb which is rubbed against your hairs and brought near a piece of paper will not attract these pieces of paper. The reason being, metal which is a good conductor has free electrons available in it. So what happens when you comb metal, you are holding it through your hand acts as a wire, and the free electrons can easily pass through your hand and your body and into the ground, which is also a good conductor. So there is an easy passage for those excess electrons to easily flow into the ground, unlike the comb where there is no passage at all. It cannot pass through the plastic. The excess charges do get accumulated here on, right? The excess charges do get accumulated on the plastic comb. So when you bring these other sort of material through to it, then they basically try to jump through air to another material, and that is why you see, that is when you see, this happens only in case of the comb. Attraction happens only in case of the comb, whereas not when you have a metal comb. Okay, now so we are going to explore some basic properties of charges. One of the basic properties of charges is, now suppose if you have a system, or if you have a particular metal which has so many charges, let's say Q1, Q2, Q3, etc. up to Qn. So there are a number of charges, and these charges, okay, they're all, let's say this is the system which has all the charges Q1, and here is Q2, here is Q3, here is Qn. So number of other charges, there is some distance between all the charges. Now these charges can be regarded as point charges, just like we regarded the objects as point objects in mechanics. When the distance between the two charges is larger compared to the size of the charges, obviously the size of the charges is very bare minimum, because you cannot see it through your naked eye, so you refer to them as point charges. So these point charges in a system, if you are supposed to find out the total charge on the system, that is the net charge on the system, is given by the algebraic sum of all the charges. So Q1 plus Q2 plus Q3, etc. up to you add all the charges, that is Qn. Now, unlike any other algebraic addition, here you must remember charges can be both positive and negative. Suppose if the charge on this is +1 and the charge on this could be -2, this could be -3, etc. up to this could be +6. So the charges can be both positive and negative. So you must take into account that it has both positive and negative charges. And just like mass or any other quantity, charges do not have direction, but they do have magnitude. So charges are a scalar quantity. Now we will talk about another basic property of charges, which we call the conservation of charges. So what will happen is, suppose you have an isolated system where you have, let's take the same example. So you have the glass rod, okay, and you rub it against a piece of silk cloth. Okay, let's assume that this constitutes a system. I refer to this as the system. This is a particular system. So I'm rubbing the piece of silk cloth against the glass rod. So there could be some 3 electrons which are revolving freely in a piece of silk cloth, or what happens, or there could be some electrons. Now when you rub them against each other, some electrons do get transferred. Let's say 3 electrons do get transferred. So what happened here? It has a deficit of or less 3 electrons, and here it has more 3 electrons because more 3 electrons were transferred. So in such a case, since the number of electrons has reduced, See, generally in any atom, there has to be equal number of positively charged particles and negatively charged particles. Now, when you are rubbing this, you see that 3 electrons were transferred to another system, another material. So the number of protons or the number of positively charged particles is no longer the same as the number of negatively charged particles on the piece of silk cloth, because it has transferred these 3 electrons to the glass rod. So here basically there are more plus, right, than minus. That means there are more positively charged particles in a piece of silk cloth now after rubbing than the negatively charged particles which were transferred to this. Hence you say after rubbing, since the number of positively charged particles is more on the piece of silk cloth, this silk cloth is termed to be positively charged. And here, since there are more number of electrons and less number, the number of positively charged particles will be less now, because you have added extra electrons. Earlier they were balanced, it was neutral, electrically neutral. Now it is electrified, you have charged it, you have transferred extra 3 electrons, so there are less number of protons or less number of positively charged particles and more number of negatively charged particles. So this object or glass is said to be negatively charged. So now, did you create any charge or did you destroy any charge? Now, since I transferred 3 electrons, can I say, I destroyed 3 electrons and here I created 3 electrons? No, that is absolute rubbish. Just like, any other conservation principle, charges can neither be created nor be destroyed. They can only be transferred. So here you are transferring the charges. They are neither created nor destroyed. So if you take into account the total charge of the system as a whole, it remains constant. So the total charge on an isolated system always remain constant, since charges can neither be created nor be destroyed. I think that makes sense. So now we are going to explore something called quantization of charge. So what do you mean by quantization of charge? The total charge on a system, can be referred to as Q. Capital Q is always given by the mathematical equation N into E. So where Q is the total charge on the system or the net charge, and N is a positive, N is an integer or the number of electrons, and E is an electronic charge. E is either the charge on the proton or charge on the electron, charge on electron or proton, and the value of E is mathematically given by 1.602 into 10 to the power of minus 19 coulomb. Coulomb is a SI unit for charge. Okay, 1 coulomb approximately has about 6.2 into 10 to the power of 8 electrons. That is a very huge number. Hence, generally, we always refer or write, the electrons or express, we don't generally express it in coulomb, because coulomb is a very huge charge. We generally express it in microcoulomb or in millicoulomb. So, micro means 10 to the power of minus 6 coulombs, or it is generally 10 to the power of minus 3 coulombs. Sometimes we also express it by nanocoulomb. Okay, nanocoulomb is 10 to the power of minus 9 coulomb. Okay, so basically what do you mean by quantization of charge? So this is the mathematical expression of quantization of charge. Quantization of charge tells that you can never have charges. N is a it's a whole number, okay, where N is a whole number, it's an integer. So therefore you can have charges. You cannot have charges in terms like half, 3 by 2. It always has to be a whole number like 1, 2, 3, etc., right? So you cannot have a half charge or a 3 by 2 charge. Always the total charge on the system has to be always a whole number. So that is basically the quantization of charge.